Good morning. I'm Kostas Kleidis. I am a professor at the International Hellenic University, and I will be the chairperson of the day. I also am an instructor, and I will deliver a lecture entitled The Nature of the Universe. Now, I would like to present the first speaker of the day, which is Professor Evstratios Theodosiou, Emeritus Professor of the Kapodistrian University of Athens and President of the Hellenic Physical Society. Hello, Stratos. Stratos, can you hear us?
Good morning to everybody. Thank you for your presentation. My talk today is toward the new theory of the unification of knowledge. So, the introduction is this. Some of the characteristics of our time are, first, the division, and second, the fragmentation of knowledge. Each and every one of various sciences defined and formulated in the beginning of the 20th century has its own boundaries and limits, is largely autonomous, and in many cases utilizes its own methods and techniques. Thus, the communication between different fields of science has become rather difficult. This state of affairs has gone beyond of the old division between the sciences and the humanities. Even among scientists otherwise belonging to the natural science, the gap is sometimes tremendous. For instance, geologists are not trained in subjects such as astronomy and celestial mechanics as they should, which are of their interest due to the precession of the Earth axis or the obliquity of the eclipses, or even other issues in astrophysics, such as Van Allen radiation zones and its probable relations with earthquakes. So we can see obliquity of the ecliptic and the precision of axis of the Earth. And down are the Van Allen radiation zones. Meanwhile, the astrophysicists are not interested in the morphology of the planets, an issue now associated with geologists. This theme repeats itself between physics and chemistry, chemistry and geology, not to mention biology, etc. Nowadays, theories of chaotic and dynamic systems and systems beyond equilibrium, which largely concern astrophysics, allow us to improve our understanding of important phenomena in various environmental studies. These studies are climatology, meteorology, ecology, and many others with astrophysics, astronomy, etc. Timaeus and Tetractys. In Plato's book, Timaeus, which is considered to be the charter of sciences, the inquisition into the nature of the universe is considered to be the source of philosophy. Indeed, in contrast with present times, the ancient Greek culture was characterized by the unity of knowledge. The Tetractys, that is, geometry, music, rhetoric, and astronomy, were in regard of one another and constituted a unified network of knowledge. Philosophy and physics. The close relations between physics and philosophy, deeply rooted in the scientific thought of the ancient Greeks, even though ignored for several years, is now making a decisive comeback. This is a book written by me for the students of physics department, The Philosophy of Physics. Relativity. The concept of relativity associated with the great physicist Albert Einstein led us to the conclusion that time and space are not independent of each other. Even since the beginning of the 20th century, the influence of this notion in philosophy has been immense, demonstrated that the disciplines of physics and science, especially, and philosophy, have several meeting points. Even more recently, the conceptual problems associated with quantum entanglement and locality became a subject of philosophical debate, in spite of such concepts being more or less something of a taboo among physicists. The discussions led to something which has not been in decades, an attempt for a scientific answer to a philosophical debate, which led to the formulation of brand new and rapidly evolving scientific disciplines, such as quantum informations and cryptography. The banner of philosophical thought led to the wide to huge advantages in our understanding of quantum theory, spurring research into new horizons. But no matter how far we venture in the microcosm or the macrocosm, the fundamental cosmological questions seem to persist. Who are we? Where do we come from? Where are we going? These questions are based on two fundamental questions. First, the what, and second, the who. The first question, what, is mainly subject to the minds of the natural scientists, where the object under observations is viewed as external and dissociated from man. The second basic question, who, is mostly regarded by scholars of the humanities, the subjective sciences such as philosophy, psychology, sociology, etc. Therefore, viewed from this angle, the relationship between the natural sciences and the humanities reflect our conception about the transcendental relation between subject and object. The subject and the object, the two basic elements of one complex enigma, pose a metaphysical question, which unfortunately does not offer itself for algebraic solution. Here, extreme ideas of physics and astrophysics can be found to supersede with talk of invisible, ineffable worlds and parallel universe. Universes like the pages of a book, making a cryptograph universe. Here are the spring theory by the species Calabi-Yau. Thus, one extreme question makes the object vanish from the equation. Our world changes, disintegrates, transforms itself. Well, to what? The answer is an imbalance of consciences, perhaps. The other extreme solution is found in the loss of the subject. Consciousness becomes but a reflection of the world. This calls for overcoming the old antinomic and restoring the relations between the parties interesting as soon as possible. Here is my personal proposal. Physicists, mathematicians, astrophysicists, geologists, chemists, biologists, psychologists, sociologists, philosophers should investigate in multi-symposia and conferences our common starting point, using themes such as pre-Socratic philosophy and modern science, philosophical questions and their answers under the view of modern physics and astrophysics. Third, a new take on Aristotle from the viewpoint of modern physics. Fourth, philosophy and natural science, ways parallel or asymptotic, etc. The truth is that the physics and astrophysics has undergone successive and productive revolution, resulting in huge boosts in various domains of knowledge. Thus, the question poses itself naturally. Can modern physics and astrophysics become a social practice and produce answers? Moreover, have the physicists and the astrophysicists the right to declare themselves as the mentors of knowledge? This is seen by some scientists as being outright provocative. In addition, philosophers who must first master the new views on time, space, matter, etc., flourish the ghost of unfettered scientism. The final proposition is the search through mutual conferences, if possible, in each domain of sciences for the elements which will contribute to the unification of knowledge and the restoration of the lost connection between the parts and the whole. Just like physics looks for a new theory of everything for all forces in nature, which will result in the unification of all known forces and natural laws, thus should sciences look for a theory of unity of knowledge. That is, which is hidden in nature must be uncovered and lead us to a better understanding of our universe, which surrounds us and of the part man has to play in it. A theory which has the power to unify philosophical dogmas with modern scientific achievements. A unity, a unification of science and knowledge, which will embrace both the microcosm and the macrocosm, as well as the scientific vision of researchers. Thank you very much for your attention.
Thank you, Stratos. Thank you very much.
Thank you very much. Thank you very much for your attention. And I thought it was, I spoke easily and loudly, and you can understand my proposal for the unification of the science, I think.
As far as I'm concerned, it was perfect.
Thank you very much. Thank you very much.
Are there any questions, guys? Do you have any questions for Professor? Yes? Yes, you. Thanks.
As you mentioned, philosophy is one of the more of the subjective sciences. Is one of the humanities. Now, in contrast, we have physics and astrophysics, whose foundings are objective, an objective perspective of the universe. While philosophy will look for an interpretation of the universe. Do you think that we could find a unified theory that is adequately universal, let's say, from our perspective, that everybody agrees on?
My presentation and my proposal is to unify all the knowledge in our studies. That means that philosophers must change their thought about their studies and to study how changes now space, time, matter, etc. The physicists and the mathematicians and the other students of the natural studies must study philosophy, because the philosophy is the element to try to understand new theories on matter, on life, on space, on time, etc. I propose that we must study all who we study natural science to study and understand philosophy, because philosophy gives us the tools to understand the new physics and the new astrophysics. So, if you are physicist, philosopher, mathematician, and you have a very good background on this, on all this, you are finally the mentor of the knowledge.
Okay, thank you very much. Are there any other questions? Okay. Yes? Sorry. Can you pass the microphone? One moment. There's another question.
Yeah.
Okay.
Do you think that scientists are really willing to do this unification, or do you think that if we try this, we will face some like consequences, like scientists scientists not really being willing to contribute to this cause?
If I understand the question is, if the science must study all of this in our studies at the university? Okay, my proposal, because it's a personal proposal, a personal presentation. I propose to study, as the tetrarch is of Plato, all the things who now belongs to the philosophical and the physics sections. So the philosophers must study all this, and the physicists and astrophysics and the mathematicians must study the philosophical things. That is, we can have many lessons in common in our amphitheaters at the university.
The boy also asked, if I understood well, he asked also your personal opinion about if the scientists are willing to do so.
My personal opinion on what?
If scientists, especially physicists for instance, are willing to do so, to get involved also with philosophy.
Well, at the University of Athens we have lessons on philosophy. That's why I write a book on the philosophy of physics, and also we have lessons on history and philosophy of science. That is the history of the science from the ancient Greeks, from the pre-Socratic times, till now, from Cartesius to the theory of everything.
Okay, thank you very much.
Thank you very much again.
Are there any other questions? I see a raised hand over there, but I think it's not a question.
Thank you very much to all.
Thank you very much, Stratos.
Bye-bye, have a good time, and always to be happy. Bye-bye to all of you.
Thank you very much. Guys,
Bye-bye.
An applause for Professor. Okay. Now we will have a 10-minute break, Kostas. Huh? No, let's have a break because I would like to. A 10-minute break. Don't go very far. In 10 minutes we will start again. Okay? I'll see you in 10 minutes. Κώστα, έλα λίγο να το περάσουμε ρε.
Για πείτε.
Θα βάλω την ομιλία.
Ωραία. Αυτό είναι για τον προτζέκτορα. Αυτό.
Μπράβο. Ωραία. Κλείστε αυτό. Ναι. Hello again.
Seconds, but not all the time playing with your mobile phones. Thank you very much.
Hello again. Now, as I told you, I'm Professor Kleidis. I teach mathematics, every kind of mathematics, at the International Hellenic University, and I will present to you my studies. In fact, it wasn't on mathematics. It was on astrophysics, and especially in cosmology. But that's why I will present you a lecture. I will deliver the lecture entitled On the Nature of the Universe. I will try to explain how we deal with the universe as a total. Okay? This is what I'm trying to do. Unfortunately, although cosmology is a very beautiful science, it needs a lot of mathematics. So, I will show you some formulas. I don't want you to understand them. I will explain them. I will take much time on explaining each equation. Okay? And at the end, I will show you how we make progress in cosmology, how we take an assumption and turn it to a theory. This is what I will try to do. I would like, I hope that you will enjoy it. Now, okay, this is how it works. The universe. What is the universe? The universe is a very big place. It ranges about 93 billion light years. That is 10 to the 24 kilometers from from one side to the other. That is, the light itself, which with the largest speed, with the largest velocity in the universe, would take about 93 billion years to go from one end to the other. And this is the observable universe. This is not the whole universe. Okay? Now, that thing contains 2 trillion galaxies. Can we count on trillions? Let's just say 1 trillion, 2 trillion, 3 trillions. Now this is a number. 100 billion trillions stars. And from now on, I will show you only exponents. 10 to the 53 kilos of mass and about 10 to the 80 atoms, particles. However, this huge amount of mass is distributed in a vast space, so the mean density of the universe is very, very small. Is this number over here, which of course you do not have to remember it, but you have to remember that it is 1 hydrogen atom per 4 cubic meters. This means that I am about 170. If I lie down parallel to you and then lie down vertically to you, I will make a cube of 4 cubic meters. Now, in this cube, there is no air, there is no dust, there is nothing. There is only 1 hydrogen atom. This is how empty is our universe. But yet, we see that it is full of filaments and galactic walls and huge intergalactic voids. Okay, this is what we call the large-scale structure. This is quite new, in fact. This, ναι. Εγώ, ναι. Στο φως εδώ. Μ' αρέσει να κάνω βόλτα γι' αυτό. Sorry for the interruption. Okay. Now, this is the universe. How do we describe the universe? There is only one consistent way to describe the universe. And this is the general theory of relativity, made by Albert Einstein, as Professor Theodosiou told you. It all began back in 1906 between two friends, Einstein and Mach. Well, Mach made a mental experiment and showed that the material background at long distances can affect, in fact, motion or inertia. Well, Einstein took this idea and said that a few years later that, the large-scale distribution of matter, in fact, curves space-time, the four-dimensional space-time. It was already, he had already made the space-time to be four-dimensional a few years earlier, but the curved four-dimensional space-time, curved by mass, by the matter distribution, affects local motion. Well, as you can see here, this is the sun, and this is the curved space-time. If the sun wasn't there, a particle or the light would travel along a straight line. But now, since the background is curved, the light or the particle bends its trajectory, which means there is no gravity. Gravity is, in fact, a manifestation of space-time geometry. So, the distribution of mass curves the space-time, and this affects local motion. Now, Einstein took a lot to conclude this thing here. His equations. These are the equations of general relativity. You cannot solve them, trust me. All you have to know is that the left-hand side of these equations are the curvature, and the right-hand side is the total amount of mass and energy. Well, this is the cause, and this is the effect. Okay? And this is a constant found by Albert Einstein when he tried to take general relativity and make it look like Newtonian gravity. Now, all we want to find out is, what is this thing? This thing helps us G mu. It is called the metric tensor. It helps us to calculate distances in a curved background. Okay. You can see it as a matrix. Do you have any idea what a matrix is? A thing on which you can put, which has rows and columns, and you can put elements in this. Okay, it's something like this. Four rows, 4 columns. Now, if you find the solution to these equations, I believe you cannot find such a solution, but if you found a particular solution of these equations, then you determine the geometry of the corresponding four-dimensional space-time. And this is what we are going to do now. Now you don't have to know anything about this, but you can see the curved space-time around Earth. As I told you, you cannot solve the Einstein field equations. You need some simplifying assumptions. Okay, the first simplifying assumption made by Einstein himself was the so-called cosmological principle. It says that at very large scales, far, far away, the universe is homogeneous and isotropic. Homogeneous means that its matter distribution is uniform, and isotropic means that wherever you look along the x direction, the y direction, or the z direction, you will see the same thing. The properties of space-time do not alter along a spatial direction. The second one year after the establishment of general relativity, was the Weil postulate. Weil was a great scientist who understand very well general relativity, and he said that, okay, still I cannot solve the equations of the field equations of Einstein. What can I do? I can suppose that the motions in the universe are very ordered. This means that when two galaxies move, their motion is very small as compared to the motion of the whole universe. As you can see, the whole universe, as you will see, the whole universe expands. And the third is the so-called equivalence principle. Okay, locally here, I must live in a flat space-time. It is flat. Okay, but only locally. Now, these are the assumptions. If you apply these assumptions to the Einstein field equations, then you will find this thing. This thing over here is nothing more than Pythagoras' theorem in 4 dimensions, but not in a Euclidean space-time, in another space-time. It is called pseudo-Riemannian space-time. That's why you do not have summation of squares, but you have also some minus signs. Well, this thing within the brackets is our space in some kind of coordinates. They are called spherical coordinates. They are irrelevant with us. This is space. So in front of space, there is a function called scale factor, which depends on time and shows us how the space evolves. Is it expanding? Is it contracting? Okay, and there is also one other parameter very crucial. This is the other parameter, k from curvature. Okay, this is the curvature parameter. Now, this is what we want to find out. What is the S as a function of time, and what is the K of the universe? If you find all these, then you know about the universe. Now, let me show what have we found so far. Well, K is a crucial parameter, and you cannot, in fact, calculate it, because the equations do not help you to do so. So you have to put it from the first time, okay, from the first point. Now, if K is positive and 1, the universe is closed. This is what Einstein wanted very much. If K is negative, the universe is open. It looks like a saddle. And if the curvature parameter is 0, then we have a very nice flat space-time. It's the most easy one. It's what we wanted to have, and in fact is exactly what we have. Now, you will say, now, Kostas, you say K here, but we see something like omega here, distinguishing between these three kind of spaces. Yeah, I will show you how this omega arises later on. Now, let's talk about the matter of the universe. What is the matter of the universe? The matter of the universe, of course, are concentrated on galaxies, on clusters of galaxies, etc., etc. But we have to impose, again, an assumption. The matter of the universe, we choose to be a perfect fluid. This means that it can be described by this quantity over here. You don't have to see it at all. All you have to know is that this epsilon is the energy, and this P is the pressure. They are very important quantities. Now, and these are the velocities. Look over here, because it is quite interesting that if these epsilons are quite smaller than the velocity of light, say, then you can write this vector, this quantity here, you can write it like this. And if you do not have large velocities, then you do not have pressure in the universe. Such universe is called dust universe. The material of this universe is called dust. It is not dust, it is called dust. Okay. So now we are ready to see our equations. Now, if all these assumptions are applied to the original equations of Einstein, then you end up with these two, these two equations. They're quite easy ones, but what are they? Now, this is the relative velocity at which the universe expands or contracts. We would like to know that. So if we solve these equations, we will find solutions for S and K, but we also need to know epsilon, we need to know P, etc., etc., etc. And of course, the velocity fields. So we have two equations, sorry, where is it? Yes. We have two equations in order to calculate 7 unknown quantities. This is impossible. We need to have 7 equations to calculate these quantities. Thankfully, again, louder. Well, if this is the velocity, this is acceleration. Okay? Very nice question. Sorry. I meant to say that, but okay. And these over here are the various universes. You will see them one by one later. Thankfully, we also have the so-called conservation laws. Well, when you go to study curved space-time, you have to be very careful. You need to change your own mathematics, because parallel transport in curved space-time, it's not always possible. You cannot retain parallelism between two things in curved space-time, because if the space-time here is curved enough, then the one thing will go something like this. Okay, so we have to find a way to guarantee that we have parallel transport. It's very important. And they, not we, they did so by inventing this symbol here, which is, this symbol here, sorry, which is the Greek question mark or the upper dot in English. Okay, now, this thing, if a quantity is followed by this symbol, then it guarantees parallel transport in curved space-time. And if this quantity, if the effect of this symbol on a quantity is 0, then this quantity is conserved. Now, this man here, Luigi Bianchi, 2 years, I believe, after the general relativity, found that the Riemann tensor and its contractions, that is, this quantity, is conserved. Its covariant derivative is 0, it means. But this quantity, it's the right-hand side of Einstein field equations. We're very lucky, because if the right-hand side is conserved, equals to 0, then the right-hand side is also conserved. And this second equation gives the conservation of mass and energy by itself. Of course, it gives us also 3 equations which are the flows of matter in the universe, and one very useful equation, which is the so-called continuity equations, which is in fact the conservation of mass and energy in the universe. Now, all you need, you see, we had 2 equations. Now we have 3 more here, 5, and 1 more here, 6 equations. 6 equations for 7 unknown quantities. Of course, you cannot find the 7th one, but you can do so if you choose the kind of matter that fills the universe. That is, if you choose an equation of state. So what we do is we put by hand an equation of state, and then we put by hand also kappa, the curvature parameter, and then solve these equations to find out in which kind of universe are we living in. Now, the first effort was done by Schwarzschild, but it was for a stellar object, and he found the well-known Schwarzschild black hole. Now, the first effort of solving the equations of general relativity was done by Einstein himself. 1 year, 1 year after introducing his famous equations. Now, Albert Einstein was a very religious man. He thought that there was a mighty God who made a universe that is closed. He cannot imagine a universe that it is not closed. Okay. He cannot imagine something outside the universe, so everything it is in a sphere, it is closed, so the curvature parameter is 1, and static, the universe does not evolve. God made us so that he can protect us within a limited sphere, and of course there were no motions, so pressure was also 0, and the energy was only the rest mass energy, which means density times c squared from the other famous equation of his. Well, if you put all these things in the field equations I showed you, then you will end up with something very peculiar. The first Friedman equation will give something like this, okay? But the second will give you that the density of the universe, the matter density, the mass density, is 0. Of course, this cannot be happening. I am not 0, you are not 0. Okay. As a result of 0 mass density, the radius of the universe should be infinite. Okay, this cannot be happening. So Einstein said, okay, I was wrong, and he tried to correct his field equations. Well, correcting his field equations, it means that he also included this term over here, the so-called lambda term, the cosmological constant. Why constant? Because it is a constant. And if you take this thing from here and put it on the other side, on the right-hand side, then you will see that it corresponds to a constant energy density, a constant energy. Okay? And this constant energy produces a repulsive, because it is positive, a repulsive, if you take the Newtonian limit, then you will find out that this it's a repulsive gravity, a repulsive gravitational force. All these are caused by the cosmological constant which was put by hand by Albert Einstein. Well, okay, now his field equations are okay, do not have any problem, and he could find a solution that the radius of the universe is reversed to the matter content. It was a satisfactory solution, but of a static universe. But the universe, it's not static. Back in 1929, yes. Okay, ξανά. Πιο δυνατά. Άνετα. Δεν μου λέτε, παιδιά, αν μιλάω έτσι μ' ακούτε? Όχι, 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 όχι. Άντε, καλά. Λοιπόν. Πρέπει να κάνω κινήσεις εγώ. Οκ, εντάξει. Θα το προσέξω, ευχαριστώ πάντως. Λοιπόν, back in 1920... Καλό είναι, μια χαρά είναι. Back in 1929, sorry, this man over here, a former lawyer, discovered that the universe expands. In fact, he said that we are living in the most hateful galaxy in the universe. His observations in Mount Wilson showed that every galaxy is getting away from us with a velocity that is proportional to its distance, which means the very far galaxies are getting away very fast. Okay, and he found his famous law, Hubble's law. This was Edwin Hubble. He found his law, who said that indeed the velocity equals to, it's proportional to the distance. And the proportionality factor is called Hubble constant, was called Hubble constant. Now it is called Hubble parameter, and in fact is the relative velocity of expansion. Okay. So the universe is not static. The universe expands. So we are looking for solutions to an expanding universe from now on. And this is here, just for the history. This thing here shows us how he found this result. It is called redshift. That is a particular line, this black line. The farther the galaxy is, the more it is transported to the red side of the spectrum. It is called redshift. Now, what does it mean that the universe expands? It means that the linear dimension of the universe increases. The spatial section, the space, is blowing. Now, at this moment that we are talking, we are getting away from each other. How much? For a distance of 2 meters, about the diameter of the proton. So we need many years to see this. We will not see it within our lives. But if you look away, very far in the universe, then you will see galaxies moving away. You will see this phenomenon. So when the universe was described that it expands, then Einstein said the famous expression that the cosmological constant was not needed anymore. So Einstein admitted that the cosmological constant was the biggest blunder. Blunder is a big mistake. The biggest blunder of his life. Now, let us describe the expanding universe. The expanding universe is also described by Friedmann equations, which now are written in this form. There is no second Friedmann equation. What happened? Well, if you combine this equation and the conservation of mass and energy, then you will see, you will take the second Friedmann equation, so you do not need it. All you need is to find a universe. All you need is the first Friedmann equation, provided that you choose a value for k, and the continuity equation, provided that you have an equation of state. You have determined the kind of matter of your universe. In this way, you can make a lot of universes. And in fact, we do have made a lot of universes. Now, which one is the correct? We will see. Well, once again, the first effort was made by this man here, Albert Einstein, and this man here, a Danish scientist, De Sitter. Well, they combined efforts back in 1932, and they found the so-called Einstein-De Sitter model, the first reliable model. It was flat, so the curvature parameter was 0, and it did not have any pressure, because they calculated the velocities of the neighboring galaxies, and they found that they are quite small. In fact, it was something like this, 10 to the minus 5 of epsilon. So they said, okay, pressure is negligible, and we don't have to include it in here. It is something like 1 plus 10 to the minus 5. So the universe they chose then, back then, was a dust universe. Okay, this is the energy and the density, and you can now define the so-called critical density. The critical density today is the density you need to close the universe, or to have a flat universe, something like this. If you have more than critical density, the universe is closed. If you have the critical density exactly, the universe is flat, and if you have less than critical density, less density than the critical one, so the universe is open. Now, if you do some calculations, you end up in here. I would like to show you this. This omega, it was the thing that separated the various universes. What is it? It's the ratio between today, the mass density at the present epoch, and the critical density. As you can see, it's 1 plus k and something constant. So if you have k equal to 1, then omega is larger than 1. If you have k equal to minus 1, then omega is lower than 1. And if you have k equal to 0, then omega is exactly unity. But omega involves the density of the universe. So if I measure correctly the density of the universe, the matter density of the universe, then I can tell in what kind of universe we live, because I will compare it with the critical density and then decide in which kind of universe we live. Okay, let's do some observation and let's measure the mass density of the universe. Now, the critical density, it consists only from constants, and we can calculate it in a, in great accuracy. It is something like this. Or 6 hydrogen atoms per cubic meter, but this is large. When we calculated the mass density of the universe at the first beginning, well, it was, if I remember correctly, 1 hydrogen atom per 4 cubic meters, and not 6 hydrogen atoms within a cubic meter. So this is large. Indeed, the matter density, me, you, the flowers, the soil, Earth, galaxies, etc., all these things contribute only a 5% on the critical density. So the density parameter of matter is very small, and certainly not unity. So, but thankfully, in universe, there is not only luminous matter, but there is also dark matter. And dark matter, it's much more than the luminous one. Well, dark matter was discovered back in 1933 by Fritz Zwicky. But he tried to understand why the galaxies in the coma cluster remain in their position. Because they were moving very fast, so there should be no coma cluster. And then he concluded that there should be some kind of matter that I cannot see. And this was called dark matter. Many years later, dark matter established itself when Vera Rubin, this lady over here, while studying the galactic rotation curves, showed that thing. If the galaxy consisted only of luminous matter, then its rotation should go in something like this. However, observation showed this plateau over here. So she imposed that there is also dark matter. And each galaxy is within an envelope of dark matter. This is correctly. Okay. Now, what is dark matter? We don't know. This is for you to find out. We do not know what is dark matter. We assume that it consists of some kind of particles that does not emit or absorb light. There are such particles. They are the particles that interact only through weak interaction. You know that there are 4 fundamental interactions: gravity, electromagnetism, weak interaction, and strong interaction. Now, that's why we call them WIMPs. WIMPs. It means weakly interacting massive particles. However, although we do not know what this is, but we can measure dark matter. How? By using general relativity, because dark matter curves the 4-dimensional space-time and causes the aberration of light. So, using the so-called gravitational lensing, or weak gravitational lensing, and too many hours of observation, we have managed so far to map the distribution of dark matter in the universe, in a large portion of the universe at least. And as you can see, its distribution looks like the one of the luminous matter. In fact, we believe that dark matter created first, and then the luminous matter went where dark matter curved the space-time and fell inside this well. So, how much dark matter is out there? Well, not much. It's only 26% of the critical density. And if you add it to also the luminous matter, and you will find that the mass density of the universe is about 0.3, 0.31, which is much lower than unity, and therefore it's official. And at least it was official until 1996, sorry. Well, it's official. We are living in an open Friedman model. So kappa is negative. But there are also other things to know. The cosmic microwave background was found by these two gentlemen. They were technicians of the Bell laboratories, and they were conducting experiments on microwaves. They had made this antenna, and suddenly they found a uniform distributed radiation in the microwave wavelength, which means that which corresponds to a temperature of almost 3 Kelvin. Okay, this is the cosmic microwave background. They found the cosmic microwave background back in 1965, and this is the remnant of the Big Bang. Well, it was the bang, the universe expanded, okay, and cooled, and at some point the atoms were formed, and the radiation started to move freely. This radiation was discovered, was received back in 1965. Now it is all. So now we have also cosmic radiation inside our universe. Okay. Back in the Soviet Union, there was a huge scientist named Yakov Zeldovich. Well, he said, okay, let's see what the primordial perturbations of density would affect, how they would affect the cosmic microwave background. And he found that the more the matter is, of course, the deeper the well would be in the curved space-time. Okay, so the more effort the photons would do to transport through that well. Effort for a photon means that it cools. So, okay, so Zeldovich said, and his co-workers said that there should be hot and cold. If you take a photo in microwaves and see this radiation, there should be hot and cold spots. Hot, not too much matter. Cold, a large concentration of matter. And what they did is to calculate the they calculate the angular size of these spots, hot and cold. Angular size, sorry. How large would they seem in an angle? And they found that both those spots would be of the order of 1 degree. Okay, let's make an experiment and try to see this, try to photograph this radiation. And in fact, we did so. Back in 1992, the Cosmic Background Explorer went upwards and took a picture of the universe in the microwave wavelength. And they found this thing. Oops, sorry. They found this thing, this kind of map. This is the whole universe with the accuracy of 1992. Well, they calculated the angular diameter of these spots, and they found that it is indeed of the order of 1 degree. So, what does it mean? Of course, it meant a Nobel Prize, but it means that we are living in a flat space-time, according to Zeldovich. And in fact, we repeated this experiment. We sent out the WMAP probe, who took a photo of the whole universe in microwaves and at much larger accuracy. And this is the image of the universe, the icon of the universe, about 400,000 years after Big Bang. So all these spots are of the order of 1 degree, which means that today the universe is spatially flat. It's flat. The curvature parameter is 0. This is definite, I want you to know. And this means that we need much more energy. Why? Because matter is only 0.3, and it should be 1. So there cannot be any other matter that we do not know, so there must be some kind of energy. And this kind of energy, it was called dark energy. Back in 1996, we all believed that the universe is decelerating its expansion. Why? Because galaxies attract each other. So the universe should stop at some time. Two scientific groups, these two gentlemen over here, professor and student, and this gentleman, well, at Cerro Tololo and at the commanding post of the Hubble Space Telescope, try to measure this deceleration, try to measure the deceleration parameter. Well, to do so, they used the supernova 1A type events. It's a very accurate event. What they wanted to do is to measure the distance and the magnitude of a source, of a luminous source, which has a well-known absolute magnitude. This is a supernova. Now, if their observations were correct, so these things should align along this line. Okay, but in fact, what they found is that the supernova were not aligning along this line, but they went that way. They were dimmer, fainter than what was expected. Fainter than what was expected, they can be achieved only by one way. They were farther. And how did they get farther? They went farther because the universe itself accelerated its expansion in the last 6.5, I believe, billion years. Okay, what causes this cosmic acceleration? Cosmological constant. No, it's not cosmological constant. Well, what they did was to take this equation and in addition to matter, they used also the density parameter of lambda, of the cosmological constant? Well, this introduces this minus sign here, which means that the denominator is smaller than the mass only. Smaller means that this distance is larger. This fits the data. All they have to do is to try some numbers for omega mi and omega lambda. And when they put these two numbers, all the supernovae were aligned along the correct line, theoretical line. Okay, so the cosmological constant not only strikes back, but it's here to stay. Why? Because there is something that could cause a cosmological constant. It's the vacuum energy. Well, vacuum in quantum mechanics has an infinite energy. Vacuum in classical physics has a zero energy, okay. But in quantum mechanics has an infinite energy. But we do not care. You know why? Because we also measure energy differences, energy variations. Okay, so we have infinite plus 1, plus 2, plus 3. Now, within this vacuum, there can be creation and annihilation of particles. In fact, at this very moment, an electron and a positron, many electrons and positrons, are created from zero and annihilated to zero again for a time that is 10 to the minus 21 seconds. In this time, you cannot see them, you cannot take them into account, they do not enter into the real world. But sometimes, as for instance, at the edge of the horizon of a black hole, sometimes they do enter inside our universe, and due to tunneling effects, this is a quantum phenomenon, purely quantum phenomenon. So they can enter our universe. Okay, so we have too much vacuum energy. Yes, and this energy may serve as compensation for the extra energy source needed to make the universe flat, because matter does not account for it, and can also account for the repulsive force we are talking about to accelerate the universe. Okay. However, there is a big problem. If you calculate the vacuum energy, then you will find out that it is, 10 to 123 times smaller than the vacuum energy. The cosmological constant is very small today. Okay, so lambda is not vacuum energy, and then what is that causes cosmic acceleration? It is certainly not lambda. And they assumed that there is a dark ingredient, a new dark ingredient, the so-called dark energy. We do not know where it came from, but we know that it is out there. So this is the composition, of the universe. Dark energy, the biggest part of the pie, dark matter, and this is the luminous matter. We only see this thing from the universe content. And then, as you can see, the dark energy is the holy grail of modern cosmology. I do know too many scientific groups working on it. There are more than 1 million papers, articles. And in 2003, because they are arguing with each other, we have arrived to an agreement, to a concordance. So we agreed that we live in a lambda CDM model. Lambda denotes dark energy, CD denotes cold dark matter, and M is the pure matter. Now, which are the dark energy candidates? Well, there are a lot of them. First of all, cosmological constant. These are the equations of states. Some mathematically oriented scalar fields discovered in order to cover this gap. Other fields named phantom fields. These universes are not real, if you want my opinion. This thing here is quite interesting. It is the gas inside a motor, inside the internal combustion engine, inside the car. This thing fits the data. And finally, the fact that the universe is described by a theory more general than general relativity. Yes, there are many such theories. So, are there any normal candidates? Are there any conventional candidates? Yes, there are. Back in 2000, two great scientists, Spergel and Steinhardt, proposed that if dark matter was self-interacting, then this energy could be attributed to dark energy. Okay, and this led to a bunch of models called unified dark and energy models. And in fact, dark matter can be interacting according to these results. Well, high energy particle detectors showed that there is much excess of electron and positron. Look here, there should be all in this thing, in this stripe, but there are many events outside the stripe. The same is here. Well, these events are unexplained electron and positron production in the universe. We have too many detectors to detect these things. So we do know that this is much more than what we expect from supernova explosions or cosmic particle collisions or other things, or gamma ray bursts and such things. So these things can be born by the collision of WIMPs, the collision of dark matter particles. So there is a possibility that dark matter the dark matter constituents interact with each other. Which means, now, what sort of interaction, we do not know yet. There are many articles on this. For instance, this article proposes that there is a fifth interaction. Now, this is where we have this is where we have reached so far. This is our universe. This is how we began from Albert Einstein and came up until today. Now, τι ώρα είναι? Τι ώρα είναι? 11? 11 και μισή. So, this is the common knowledge. What I'm about to show you now, it's how you make new theories for the universe. But at this point, I believe that you are quite tired. Πιο κοντά? Εντάξει. Thanks. Well, I believe that you are quite tired. We will make a 5 minutes break, okay? And we will continue for the next half an hour or so, okay? See you in 5 minutes.
Φυσικά. Περιμένω.
καλό.
Ναι.
Γιάννη, να το πάρω αυτό. Και η κοσμολογία της πήρε. Παιδιά, μπορείτε να το βρείτε εδώ, μπορείτε να το βρείτε εδώ. Τι μπορείτε να σπείτε αν σας άρεσε, όλα αυτά υπάρχουν εδώ.
Τώρα θα τα πει
Κάπως καμιά πατέντα μόνο, αν πούμε. Κάπως,
Ωραία.
Ωραία.
Ναι. Αυτός. Θα τον αφήσω εκεί, οπότε κατεβάλει στο βάρ. Έτσι.
Βλάτε, πού έχουμε βάλει το τέτοιο, αυτό που αλλάζει τις διαφάνειες.
Εδώ το έχετε.
Μετά, όταν στο διάλειμμα.
Εγώ γι' αυτό είπα είναι δυνατόν να μεταφερθεί το...
Και πάλι ψηλό είναι.
Όχι, δεν μπορεί να μεταφερθεί.
Καλύτερα εσείς.
Δεν κρατάει το μικρόφωνο. Βάλτε την γυναίκα να κρατάει μικρόφωνο.
Guys, shall we begin in order to end? Τα είχα ανοίξει. Α, αυτό είναι ωραίο. Ωραίο κόλπο, ναι. Now, guys, well, now I'm going to show you how you create a theory. You take into account several things, such as those I already showed you, and you put your own signature, your own contribution. So, we are fond of conventional solutions. And when I say we, it's me and the next speaker. It's Professor Spiro. So we took the idea of Spergel and Steinhardt and said, let's find a conventional solution to the dark energy problem, to the dark energy concept. Is there anyone? So, in fact, there is, and this is a catalog of articles that led to this conventional candidate. Now, our contribution again. Let's impose that the WIMPs, the weakly interactive massive particles, interact quite often. In this case, their kinetic energy is redistributed. That is, it fills the void, it fills the whole space. And in technical terms, it is called the universe has a thermodynamical content. Now, if there is such a content, again, then yes, there is a conventional candidate for dark energy. And it's the energy of the internal motions. As the fluid of dark matter flows into space, moves into space, its internal kinetic energy is redistributed and appears as dark energy. Okay, now this is the thing. So we assume that we live in a universe, a spatially flat universe, which does not have any dark energy at all. What it does have, it has ordinary matter and dark matter. Only this. These two things form a fluid, perfect fluid, which performs, the elements of which perform polytropic flows. When I say polytropic, it's in fact an equation of state. It's something that connects pressure and density. So instead of being pressure equals density, as it is the well-known ideal gas thing, in this case, pressure equals density to an index which is called polytropic index. Well, we found that this polytropic index is in fact something very small in a very narrow range. It's something between 0 and minus 0.1. Okay, if this polytropic index is 0, then we have the well-known, the well-admitted, the established, or not, lambda CDM model. Our model is isomorphic to this model. So our model can recreate lambda CDM model, as you will find out immediately after. Now, instead of admitting that, oops, sorry guys, instead of admitting that that the energy is caused only by the mass term, the matter density, so we impose that there is also another term, the internal motions. And we can, in fact, we can find this thing by using a very famous law of physics, the first thermodynamic law, and then the final form of the energy in the universe, of the energy contained in the universe, is this. Is this. Okay, apply it. Try to apply it for the present epoch. At the present epoch, we have S equal S0. S0 its present value. So if you do so, and calculate the density parameter, then you will end up with exactly what? 1. The polytropic model does produce dark energy, although it's not dark. It's the energy of the internal motions of the volume elements of the fluid. Okay. So, okay, this is not the only prediction that is, this is not the only prediction about dark energy models. See this. Now, this is the solution for the scale factor. Do not see, please do not, no, sorry. Do not look at the formula. Please look at this thing. Now, this is the plot of this formula. What does it tell us? Look here. The universe is created from 0, then it expands, decelerating, and finally, around here, that is quite recently, as it should, the plot becomes concave. It takes a sort of bell shape, which means from here, the universe accelerates expansion. So this model also explains the accelerated expansion, not only the dark energy. And again, not only that. Well, this is the deceleration parameter. It should be negative in order to have accelerated universe. As you can see, at early epochs, it is positive, a decelerating universe, okay. But today, Z measures distances and time, in fact, which is the same thing in the universe. Z equals 0 means here and now. So today, the deceleration parameter is something like this, which for gamma equals 0, let's see if it fits to the lambda CDM model. For gamma equals 0, the deceleration parameter becomes this, admits this value, which is certainly within range found by observations back in 2012. So also the deceleration parameter can be explained by a polytropic model. And again, the transition redshift, that is something around 0.7, at that epoch happened the transition from deceleration to acceleration. Well, the deceleration, the transition redshift formula in our case is is this, and when you put gamma equal to 0, you take this result, which is exactly the result of lambda CDM. Once again, it can reproduce lambda CDM. And the age of the universe, in our case, for gamma equals 0, is this thing, okay. It gives 13.8 billion years, which is exactly the age of the universe in the lambda CDM model as established by observations. And there are many ends. No, you don't have to know this, but it is exactly, once again, it's the lambda CDM result. This is called effective equation of state. It's the ratio between pressure over energy. It should be something around minus 0.7, and it is exactly this one, minus 0.692. Once again, the lambda CDM result. And, now this is something different. This is not a coincidence, which means, is our model consistent with itself? Okay, let's find out. Now, let's change our optics. Let's take the second, the second Friedman equation, where is it? Nothing. There it is. And consider what would happen if we have an accelerated universe. Well, in order to have acceleration, S double dot should be positive. And this means that the right-hand side should be negative. Well, if you put where epsilon, the one found in the polytropic model, and P, the one found in the polytropic model, then you will result with this formula, which is nothing else but the transition redshift, which in our case came out from our admittance that Q is negative. So it is a perfectly self-consistent model. One equation leads to another and to another and to another in a perfect circle. Now, how did we determine the polytropic index? Well, we took a polytropic fluid of 0 pressure. This led to gamma lower than unity. We took that the transition to acceleration happened earlier than today, which is logical. So gamma became lower than a half. Then we admit a stable perfect fluid. That means this thing here, it's always positive. Now you will ask if this can be negative. Yes, in some kind of numbers you will find out quite later. And this led to the result that gamma it's lower or equal than zero. And finally, we admitted that the dark matter is cold. It means it does not move quickly. So this led to the fact that gamma is larger than this thing, than 0.1. And finally, this is the range of gamma. Well, in fact, this is also compatible with the results of this scientist here. This scientist obtained his results for the lambda CDM model. And this is the final one. No, it's the pre-final. This is the distribution of supernova in our model. Please tell me, what do you think? Does it fit well or not? And these are quite many events. I think it's much more than 580 that used by them. So, as you can see, it fits, the theoretical curve is this blue curve, fits the entire population of supernova quite accurately. This is not lambda CDM, this is our. Okay, and finally, yeah. This is a spectrum of primordial perturbations, is the fact we look at the universe and see the distribution of galaxies and then make assumptions on how did they become the way we see them. So this is called primordial perturbations. When the Planck satellite measured this distribution, it found out that it was it has a spectral index, this one. This can be done also theoretically, and me and Professor Spirou did it also theoretically, and we came up with this curve, which fits this line almost perfectly within the horizon, which means that our model also predicts the same distribution of large-scale structure, more or less. So, summarizing. Summarizing, in the reasoning of Occam's razor, Are you familiar with this expression? Well, Occam Razor says if all turns to be equal, then the simplest explanation is the correct one. So in this reasoning, since it is equal, everything is equal, it's possible that the well-known and admitted lambda CDM model, it's nothing but a polytropic fluid model with polytropic index equals to 0. Okay? And this is the universe. Can you see it? How it looks like to our scale factor? The universe begins over here, then after inflation, it expands with deceleration, and at this point, the bell shape, the universe accelerated its expansion. This is the bell-shaped curve I told you about. So, guys, boys, girls, thank you very much for your attention. And remember, the truth is out there. Okay, thank you. So now, we will... ναι, θα πω. Το μικρόφωνο. Before we make a break, in order for Professor Spirou to get ready for his speech, are there any questions? Yes, I was expecting that.
What further observational data would be needed for something like that to be confirmed, and it would not confirmed and further supported? For any model, nonetheless, but especially this one.
Okay, since we are talking about our model, I will talk about this model. No, there are no other any other observational data needed. No, nothing. These are all. All we need in order to be further established. It is one of the models that considered as a model of dark energy today, is our model. Well, what we need in order to get further established this model is an explanation why you need a polytropic model. Why polytropic? What does it mean quantum mechanically? What sort of particles would flow in order to make a polytropic fluid? This would be excellent. And in fact, we are working on this at the moment. Anyone else?
I think we are okay. Thank you.
Thank you very much. Thank you very much, guys. 5 minutes break. 5 minutes break in order to
If we are ready, we can start. Please sit down.
Από εκεί ήταν. Τα έχω κλειστά τα μικρόφωνα. Και αυτό είναι ανοιχτό.
And now, hello again. Now I become once again the chairman. Well, now we are going to attend the final lecture of the day before noon, and I call to the stand Professor Nikolaos Spyrou to deliver his lecture.
Thank you, Kostas, for your introduction. For the invitation to give this lecture, I wish to express my sincere thanks to Dr. Kostas Voulias, to the host American Farm School in Thessaloniki, and to all the organizers and co-organizers of this summer school, the main objective of which is to promote the idea of teaching cutting-edge astronomy and astrophysics and physics in the Balkan schools. The purpose of this comparatively short closing lecture is to offer to you, the younger generation, some interesting messages concerning the appropriate method for study and research, particularly in cosmology, and more generally in astronomy and astrophysics. And for such a purpose, you, the younger generation, are the appropriate audience. I have to say in the beginning that Professor Kleidis prepared in the best way my lecture, especially as far as our contribution to cosmology is concerned. And I thank him very much for this. I shall not show you any mathematical relations or detailed tables or composite figures, mostly unnecessary. Only some very simple and easily understood slides will be shown. For those of you interested, my lecture will be available in electronic form very soon. If you want me to send this lecture to you, You can use my electronic address, spiro@auth.gr. Just a moment. I also have a pointer here. Well, in spite of this, however, I wish to kindly ask you to pay attention to the useful message I want to pass to you, particularly to those of you interested in future work in the broad astronomical cosmological era. And this useful message refers to the way physics and mathematics, as two entirely different areas of knowledge, should be used in a realistic description of the cosmological universe, namely a description that is also physically, not only mathematically oriented. This message is closely related to a very useful personal experience of mine since the early 1970s, the time of my doctoral thesis. Kostas, please, next. As the late Professor Sir William Hunter McCrae said in his presidential address to the Royal Astronomical Society, I am always surprised when a young man tells me he wants to work at cosmology. I think of cosmology as something that happens to one, not something one can choose. In other words, working with cosmology is not something to choose between other possible choices. Working with cosmology is something coming from your inside. And it is not possible to abandon cosmology, even for many reasons, if you are forced to do so. This is exactly the case with the present speaker, who started his research with cosmology, and after making a necessary tour to many other astronomical research areas, he returned to cosmology. Beyond this truth, it is very useful and helpful for you in your interactions with other scientists to remember also the following two truths. If you can't explain it simply, you don't understand it well, said Albert Einstein. And the equally important, the greatest enemy of knowledge is not ignorance. It is the illusion of knowledge, as Steve Hawking said. After these introductory and informative remarks, and as you probably know, cosmology is the science aiming at the study of the universe as a whole, its beginning, its evolution, and its possible end. The study of cosmology, as of every other physical scientific area, is based on the mutual interaction between theory and observations experiment. Suppose that we wish to study the dynamical behavior of a physical system. This system can be, for example, the atmosphere of the Earth, or a star and its evolution, or a galaxy and its properties, or a system of galaxies, or even the universe as a whole. In the dynamical description of each one of these physical systems, in simple words, we use an underlying, well-established theory that makes certain theoretical predictions. In cosmology, this theory, as Kostas told many times, is Einstein's general relativity theory. Now, the predictions of the theory used are either verified or disproved by the observational results. If a prediction is verified, the theory is enhanced and proceeds to another theoretical prediction and to another one, and so on, with this procedure being applied to all, not only to one or a few of the available experimental observational data. But even if only one prediction does not agree with the experiment and observational results, then the whole theory collapses. It is rejected, and if possible, it must be improved as regards its main and basic assumptions. This is, and this should be, the usual way scientific progress proceeds. Notice that so far, no astronomical, cosmological, theoretical prediction of relativity theory has been disproved. Up to now, all of them have been verified by observations. This is something that you have to take seriously into account. No prediction, no relativistic prediction has been disproved by observations. Furthermore, it is obvious that necessarily for the research to be realistic and reliable, the theoretical predictions and the corresponding observational data themselves must be reliable. Well, reliable observational data, what it means? It simply means that the presented data are not, say so, cooked. Namely, they truly express what the observations have revealed. But also, the underlying theory and the corresponding theoretical predictions must be reliable from both the mathematical point of view, the mathematical point of view and the physical point of view. And at exactly this point lies the most serious problem concerning the way the cosmological research is done. Namely, up to now, the cosmological research has been only mathematically oriented, but not at the same time also physically oriented. This is known long ago. Einstein himself had noticed that as far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality. Let me be a little more precise and detailed on this. In describing the universe as a whole, we have many reasons to assume that on the very large scales, the content of the universe is in the form of a continuous medium. Professor Kleidis emphasized that we are not referring to a system of galaxies simply which each one has linear dimensions almost negligible compared to the mutual distances of neighboring galaxies. Namely, the universe is not an empty space, but instead it is a continuous medium. Here you can see the Milky Way, our galaxy, and what I show you this here is its optical picture of the galaxy. And here are the two neighboring galaxies, the Large Magellanic Cloud and the Small Magellanic Cloud. However, with the existence of dark matter, this picture changes. Namely, really, the galaxy is at least 20 times larger than its optical appearance. And in the next slide, you see here is Milky Way galaxy. 30 kiloparsec are the linear dimensions of the galaxy. And here is the closest galaxy, the Andromeda galaxy. And you see that each galaxy extends up to 200 kiloparsec, and the same for Andromeda, so that the two galaxies are almost in contact. This is what I told you as the continuum space, continuum universe. This continuum universe is composed of various forms of mass and of various forms of energy. The mass, both baryonic and dark, is gravitational. Namely, it creates a field of the familiar attractive gravitational forces which tend to shrink the physical system under consideration. Also, it is known that any amount of energy, epsilon, corresponds to an amount of mass, and these are related by the famous formula epsilon is equals mc squared, which is a very known result even to this little girl. Namely, energy creates gravitational field. Energy creates gravitational field, not only the mass. Given all this, the cosmological medium dynamically can be treated as a continuous gravitational physical system, a gravitational fluid, and this fluid is called the cosmic fluid. Notice, however, that until very, very recently, in the cosmological research, all forms of energy of the cosmic fluid have been ignored and omitted as sources of the universal gravitational field. In all the theoretical cosmological treatments and theoretical results, all these forms have been tacitly assumed and omitted, and only the mass has been taken into account. What taken into account means? The dynamical, thermodynamical description of such a gravitational fluid is very well known. And in this context, the cosmic fluid is the cosmic fluid is characterized by many physical thermodynamical characteristics and parameters like the Young's density of matter, thermodynamic pressure, temperature of matter, heat quantity, heat capacity, thermodynamic transformations, polytropic transformations, internal thermodynamic motions, internal thermodynamic energy, entropy, etc. Is it true that some of these are known to you from the subject physics of fluid taught in high school? Is it true? Are they taught such subject concerning fluids, for example, in your schools? Yes? Please loudly, so as to be heard by anyone here. Ναι, yes? Να το πω εγώ εντωμεταξύ. I know that in Greek schools, in the corresponding books, there is a chapter on physics of fluid, but I don't know if they are taught, really.
I'm not sure either, because I haven't yet reached third grade of high school, but subjects such as density of matter and temperature of matter and heat quantity are taught, but I'm not sure about the specific like subject you referred to, because I have not yet I have not yet reached the third grade of high school.
Okay. Perhaps it's somehow early. For you, yes, okay.
In Greece, not anymore.
Sorry?
In Greece, they don't teach now. We don't teach.
They do not. They are not taught. Well, the relativistic dynamical description of the cosmic fluid is based on the use of the so-called field equations of the relativity theory. The important feature I want you to notice of these equations is that beyond mathematics, namely the tensorial mathematics used, these equations contain two important physical parameters of the cosmic fluid: the thermodynamical pressure, P. Next. Yes, thank you. And the total mass energy density of the fluid. At exactly this point lies the above-mentioned problem with the research in cosmology, and since long ago, this most serious problem appeared as follows. About a century ago, in 1932, two great scientists, Albert Einstein and William de Sitter, proposed a solution to the field equation describing the cosmological model of the universe, the so-called Einstein-de Sitter cosmological model. This model, however, in accordance with the prevailing ideas, cosmological ideas a century ago, is composed only of mass. Namely, it has no thermodynamical content. In other words, in the Einstein-de Sitter model, the thermodynamic pressure of the cosmic fluid is zero. Its thermodynamic content is totally ignored, and so quantum physically the cosmic fluid is simply dust. In their two-page long paper, the two scientists then argued. It seems certain that the pressure P in the actual universe is negligible compared with the material density. The same reasoning, however, holds if the pressure is not neglected. And so, and also, they concluded, for the sake of simplicity, we neglect pressure. These assumptions, a century ago, were not strange and were in accordance with the then prevailing mathematically oriented philosophy in cosmology. And they expressed the agony of the theoreticians at last to find a cosmological model of the universe. The strange thing, however, is that after whole a century, this model, based on the above assumptions, has been in use until very recently. And especially, the universe was considered as dust, with, however, not any problematization at all for this and for its consequences. I could say that this is like assuming that the air in this beautiful lecture hall is composed of only particles with mass, nothing else. Or it's like assuming that the Earth's atmosphere has no pressure. It is dust. And we are not interested in its consequences in the preparation of, e.g., a reliable weather forecast. Based on the simple law of perfect gases, can you imagine what really means a vanishing thermodynamical pressure in this lecture hall? What it would mean? It would mean a vanishing temperature. Whence one could ask, how we remain alive although frozen at absolute zero? This exactly is the spirit of the joke of the day I found about, well, in 1987 at the University of Cambridge. This was written by an undergraduate or postgraduate student. Did you hear about the guy who got frozen to absolute zero? He's okay now. Well, from the physical point of view, it is truly disappointing and curious that until very recently, really very, very recently, to the above note in the paper, in the two-page paper of Einstein and de Sitter, not any special attention was given at all, especially to the fact that the cosmic fluid had no pressure. The consequences of these assumptions are very important and had prevented cosmologists from solving many current cutting-edge cosmological problems. I shall mention only one widely known problem that is related to the composition of the cosmic fluid. In the context of the Einstein-de Sitter model, among many others as the vanishing pressure, only the baryonic or luminous matter was known and taken into account. Later, with the discovery of the dark matter and given many other observational data, the Einstein-de Sitter model took the form of the currently prevailing cosmological model. This cosmological model, this prevailing cosmological model, with generally vanishing pressure, consists of 5% of mass energy baryonic or luminous, 25% of dark matter, and the rest, 70%, exotic and totally unknown, was given the name dark energy. And this dark energy was denoted by lambda, which lambda characterized this lambda CDM cosmological model. Notice that 95% of the mass energy content of the universe is unspecified. Unspecified. The only characteristic we know is the luminous, baryonic matter. Also, however, notice that in the lambda CDM model, an unknown, the cosmological constant, is used to explain another unknown, the dark energy, a really absurd situation. The way out of this dead end was revealed about 13 years ago, as Professor Keleidis mentioned it, and only when all the above-mentioned physical thermodynamical characteristics of the cosmic fluid have been consistently taken into account as sources of the universal gravitational field. Particularly, the matter, baryonic and dark, is not there standing immovable and frozen, as in the lambda CDM model, but quite physically, it is characterized by collisions of their constituent particles, so that the kinetic energy of these particles is redistributed, with, as a result, the universe to acquire the properties of a continuous thermodynamical medium. This is the polytropic model with collision and thermodynamic content. And this is not the lambda CDM model, but the PC CDM model. PC means polytropic and collision. This model, the PC CDM model, is a much more physical and also much more complex and difficult fluid to treat with, in the sense also of the much more difficult and time-consuming preparation of your original scientific publications. In it, the PC-CDM model, however, almost all the current cutting-edge cosmological problems were confronted successfully in a self-consistent and classical way. Such problems, such problems are the spatial flatness of the universe. Notice what I say here. Open problems in the lambda CDM model definitely solved in the PC CDM model. Definitely solved. The spatial flatness of the universe. The dark energy. What is the dark energy? The dark energy is simply the internal thermodynamic energy of the cosmic fluid. That is quite simple. The interdependence of dark matter and dark energy. Up to now, dark matter and dark energy are considered as two entirely different and mutually independent notions. And the same holds for the corresponding research. Research for dark energy, research independently of dark matter. However, in the PC-CDM model, the dark energy is simply a physical property of the dark matter in exactly the same way that the thermodynamical pressure of a fluid is a physical property of the matter, of the density of the fluid. Well, the no dimming of the distant supernovae. Aha, this is quite important. The whole idea of the accelerated expansion of the universe was based on the observations of a certain type of supernovae called the supernovae 1A. And the result was that this, please, Costa, give the next. Yes, okay. Here is each one of these dots is a supernova, okay? And here we have the distance and the redshift. Notice here the dotted line. The dotted line. This dotted line is the theoretical prediction of the lambda CDM model. And you see that the supernovae who are far enough, they have large redshift, appear all to be above the theoretical prediction of the lambda CDM model. Why this happens? Because the universe accelerates its expansion, and therefore the universe took them there. This was the first, and I would say the main idea for the accelerating expansion of the universe. However, if you repeat the calculations, these calculations, in the context of the polytropic cosmological model, you see that no problem appears for the distant supernovae, and therefore it has no meaning to talk about supernova dimming. In the next slide, there is a reasonable question. Why why the dimming occurs only in the distant supernovae, but not in anyone else celestial object. Why only on this? Nobody claimed this dimming for galaxies, for stars, for. The answer is because simply the dimming does not exist. It is a misinterpretation of the observational data, and as such, it is an illusion, a fallacy. It is neither a physical reality nor a physical necessity. Next. Good. Then, how can we explain the acceleration, the cosmic acceleration? Very simply, assume you have a certain volume of the cosmic fluid. In it, we have the gravitational forces due to which this volume tends to shrink. But at the same time, we have the forces of the pressure which tend to expand the volume. In the initial stages of the universe, the gravitational forces took over, and we had cosmic deceleration. After a certain point, when the characteristics of mass and the characteristics, pressure and other thermodynamical characteristics, became almost comparable to those of mass, the cosmic expansion turned to accelerating expansion. And in this way, we explained also the exact time, namely the redshift, at which this reverse from deceleration to acceleration happened. We explained the coincidence problem, why this happened now, namely a few five billion years ago, the age problem, and of course the cosmological constant, which has to be left dead in its grave. Next, please. I'll show you a few slides showing. Yes, 5 minutes, yes. The research on dark energy is impressive. And what is especially impressive is the multitude of the mathematical ideas of what dark energy is. Only a few names: quintessence, K-essence, phantom cosmology, all this, and many others. In the next slide, also, during the decade of 1980, the publication frequency of papers on modified gravity was one of the ways to explain the acceleration. What was the frequency? One paper published per hour worldwide. One paper per hour, which, of course, is a result astronomically useless. Next slide. Yes. Next slide. No, ask the question. Yes. Here, all of these problems which have been definitely solved in the PCDM model are solved with the aid of only classical general relativity theory and classical thermodynamics, with no need at all of either quantum theory or modified gravity. This also is very important. Next. Okay. On all the above, oh yes, please. Loudly, loudly. Just one, Kostas. Later. You will ask me after that. Well, this is the latest paper with Professor Claidis, and many interesting and useful information on this subject you can find on the site agapakis.eu. agapakis.eu. Well, closing this short talk, I suggest that you remember first what Professor Bacret said. Second, that you must always, next Kostas, please, ναι, ωραία, αυτό μας τα είπε, ναι, εκεί. You must always have the courage to say and defend your free but well-established opinion. This is, I found in the University of Chicago 46 years ago, and you see this is the, say, research. Impressive photographs, nor simply a powerful electronic computer, but beyond and above all this, firstly and mainly, it is physical thought, physical way of thinking, physical realism, namely and in short, it is physics. And before thanking you, have you all visited Noises? Yes. Yes. Next. Then you must appreciate this photograph. 70 years ago, there are two young boys in Fort Worth, Texas, with space helmets for the planetarium showing. This is teaching astronomy since the childhood. And that's why children like this went to the moon. Thank you very much. Well, you and any other else who had questions, please come here.
That's what I was about to say.
Yes.
Because we don't have any time, the children must go to eat, must go to the restaurant. Because, and 2 o'clock, yes, here again.
Yes.
Yes.
This model,
Yes.
I think it's become my new interest. So, like, if I have anything, could I possibly ask you for your opinion?
Yes. You know my name.
Yes.
SPYROU at our year. Yes, please write and remind me that you asked. Okay?